All right, hello. Here is your walkthrough of Lab 12 on comparing many means. So just like we've been doing tests of one proportions, two proportions, many proportions, this is a test of one mean, two means. It follows with many means. So question for this lab is, do we have salaries that differ by position? So if we have our data here and we look at batting averages is the first question that vary by position. So here's an sample from our data. We have different positions, different batting averages. There's a picture has like a 0 batting average, kind of makes sense. And here are the different codes for the different positions. And so we can find out the batting average of each group by taking batting average equals double equals position. And if I run that code, it tells me for each given position, for each given player, player 1, 2, 3, player 1 is not a first base, 2 is not, but eventually there are a few first basemen. This person's a first baseman, this person's a first baseman. So those are all the players that I want to consider their mean of. So if I take the mean of that averages, I'm taking the batting average of those given players, I can find that batting average. So to find all the batting averages for the different positions, we just have to change the code here, the 2B. For designated here, the code is PH. And we can see, hey, yeah, there is a difference in the batting averages. The real question is this a statistically significant difference? Does it appear to be different enough based off the sample we have? So just by looking at the data, do you think there's a difference? And then we can look at this data here in a collective way using a box plot, which we're doing box plots of batting average by position. So this plots many, it understands that I'm looking at a numeric variable and a categorical variable. So for each category, the different positions, it plots a box plot of batting average. So that's pretty cool. You can see, it looks like there's some variation, especially for pitchers. So that tells us that I think there's a difference more than due to chance. So the way we test this question is we look at the assumption that they're all equal. We just assume they're all equal. And if that is true, we can find a statistic called the F statistic from this ANOVA test that will test the probability of observing the data that we have, given that they are actually all true, or are actually all equal. So the opposite of that would be saying, hey, they vary across position. So here's a function that just does it for us. As long as we put numeric variable versus categorical variable, and then we list our data variable here, you can get a summary of our ANOVA analysis. And of all this, we got our different statistic. Here's our statistic that it found based off some parameters. It found the probability of observing what we did is 2 times 10 to the negative 16. A very, very small number. This code tells us that it's between 0 and 0.001. So based on this, p-value getting so small, kick H naught out the wall, over the wall. So we reject it. So in context, what does that mean? That means we have evidence that the batting averages are not the same. Oops, like it appears they vary. We have significant evidence that it varies. I should say that that's more precise. We have five positions. So according to each position, the average is going to be different. So to conduct this test, there are some assumptions we want to check. Independence, is it a simple random sample? We want to say, for a big sample, do we have approximate normality for each group of batting averages? And is there constant variance in each group? Oh, the variance in each group, is it equal is it vary from, is the variance the same in each group? So to evaluate these assumptions, we can look at a histogram of these averages. So is this data normal? That's the first question. Is it approximately normal? And is the variance constant? That means for all the different histograms for each position, are they varying the same? Are they about spread apart the same? So we can roughly check that by looking at all the positions. But you can see for the pictures, there's something going on. It's not really normal. But to do this for another variable, say, do we do first base first? Yeah, we can do second base. Just change this to second base. And then we're going to want to change our title to so you do that for all the positions, third base, and so on. That's how we could look at these histograms for each position. And maybe I don't need that many breaks. I could say 20 if I want to get a smoother graph. Yeah, there you go. Very good. So assumptions, they're always good to look at. But for the sake of this class, let's focus on making sure we have the analysis. Here's another data set for the Major League Baseball players of their salary. And so we import that and we can see for each player, we have a different salary. Notice these numbers are measured in thousands. So we would take this number and multiply it by 1,000. So 8.5 million. So what is the mean salary of all our different players? Since our data is stored in Sal, I'm just gonna look at the mean of Sal. And if you run this right here, it says, hey, I don't know what to do because actually this Sal variable is all this information. I actually want just the salary variable, so I should say $sign salary. That's the numeric. So that's the mean salary, about 3.2 million. Take that number, multiply by 1,000. So if we look at pictures, do they make more or less than the mean? They actually make less. 2.999 million. So it's a little less. Maybe they should form a union and protest. 2.99 million is not enough for me to make. People seriously think that way sometimes. Okay, so here's the plot, side-by-side plot. Salary is a numeric variable, position is a category that we're comparing against. And see, do you think there's a difference? Tell me, which position seems to be making the most out of all this? And then, do we think any observed distance is due to chance? That's our hypothesis. I would say yes, but to test it, we have to use the null hypothesis that says positions do not vary. Salaries do not vary. So the mean salary is the same for all positions. They're all equal. And the alternate says they do not. They do vary. Okay. So now to conduct our ANOVA, let's just go copy paste where we previously did our ANOVA analysis here. It's this bit of code here. And copied it. Keyboard sometimes. Give it a second here. Bang on it a little bit. Okay, so here's what changes is we got a different data set, salary, and our formula here, instead of looking at batting average position versus position, we're looking at salary versus position. There's our analysis of variance. And there's our p-value. So you can interpret that. P-value getting so small. KH not over the ball. And then for your last analysis, I think we're looking at the salary vary by team. Well, copy paste the ANOVA code. And instead of looking at salary by position, we're looking at team. And if that is the correct variable, I can look here under salary and see team. Yeah, that's the name of the variable I want. So we can see, do they vary by team? You can interpret that result in context. There's your p-value. Okay, that's all. Hope that helps. And we'll see you next week.